Yes, hello friends. Welcome back to the video lessons on electronic measuring instruments. We have been discussing about electronic voltmeters. We have seen what is an electronic voltmeter, what is the block diagram of an electronic voltmeter, what are the various parts of an electronic voltmeter, and what are their functions, and finally, what are the advantages of electronic voltmeters. The next one is FET input voltmeter. An FET input voltmeter is an electronic voltmeter making use of FET at the input. In place of FET, if transistor is used here, then it would be called as transistor type electronic voltmeter. Here this is FET input electronic voltmeter. This is a commercially available, the internal circuit of a commercially available electronic voltmeter, and you can see a potential divider with three different resistances: 9 mega ohm, 900 kilo ohm, and 100 kilo ohm is being used at the input of two terminals of the device. Here the unknown voltage to be measured is connected here across this 10 mega ohm resistance. 9 mega ohm, 900 kilo ohm plus 100 kilo ohm, that is 1 mega ohm. So across 10 mega ohms, we have to apply the unknown voltage, and depending upon the range switch, the internal resistance to the circuit would change. When the range switch is in this first position, this voltmeter can be used for the measurement of voltage range 0 to 5 volts, and of course input impedance is 1 mega ohm. When the range switch is in this position, 5 volts position, the circuit can be used for the measurement of 5 volts. And what would be the input resistance then? This pointer connected here. So from here, positive of the supply through 9 mega ohm through 1 mega ohm, it will enter to the FET amplifier. So internal resistance is 10 mega ohms. So for a 5-fold increase in input voltage range from 0 to 0.5 volt to 0 to 5 volts, 10-fold range, sorry, the input resistance also is increased from 1 mega ohm to 10 mega ohm. Then for the switch in 50 volts position, the input resistance is 9.1 mega ohm in series with 1 mega ohm. So 10.1 mega ohms. So this is about the voltage divider part. Then this input, that means actually an electrical current would result here because of this input impedance and this excitation, and that electrical current makes the device to be active or conductive. Now here this FET is operated in source follower mode. You can see load is connected to the source of the FET. So we'll say it, the FET is used in source follower mode. In source follower mode, whatever is the input at the gate, the same would be the input here at the source. So whatever is the input voltage, the same voltage appears here, right? Now, you can see a transistor operated by the output of FET. So when there is sufficient voltage at the input of FET, the same voltage would appear at the base of transistor, and here the transistor is of PNP type, and here an N-channel FET is used. So based on the voltage at the base of the transistor Q2, the transistor resistance will change. The on resistance or conducting resistance will change. And you can see a Wheatstone bridge here with 4 ohms as 2.2 kilo ohms 1 ohm, 2.5 kilo ohms second ohm, and 10 kilo ohms third ohm, and the on resistance of Q2 as fourth ohm. Now, between the output terminals of this Wheatstone bridge, that is from the emitter of the transistor Q2 to the junction of the resistance is 2.5 to 2.2, a measuring instrument, a current measuring instrument is placed. This is in series with a multiplier resistance. So this is nothing but a voltmeter. A voltmeter with a multiplier, adjustable value of multiplier. The multiplier resistance can be adjusted. Now, let us assume initially that this pointer is, the switch is closed. And let us assume that there is no external voltage applied here. When no external voltage, no voltage will be at the gate of Q1 or base of Q2. So this transistor would be in off state PNP. So this is 0. N2 P. I'm sorry, my eyesight is weak. It seems it is an NPN transistor. So when 0 volts is there, this transistor would be in off state. So depending upon the relative magnitudes of resistances, that is the off resistance of Q2 and this 10 kilo ohms, and depending upon this potentiometer resistance value starting from 0 to 2.5K and 2.2K, you would get certain potentials here, and the difference of potential is the one which drives this pointer in the movable coil assembly in the instrument. So initially with the switch S closed and with no external input signal, this potentiometer 2.5 kilo ohms is adjusted slightly till this instrument reads 0 volts. The instrument reads 0 volts. That is why this is called as a zero adjustment part. And this is called as calibration part. When zero point 0.5 volts is applied here, then by adjusting this part, when zero point 0.5 volts is applied and when the range switch is in position 0.5, then this potentiometer is adjusted in such a way that the pointer reads full scale. This is calibration. Similarly, when 5 volts is applied and when the range switch is in 5 volts position, this pointer is adjusted further to make sure that the pointer is this potentiometer is adjusted so that this pointer is at full scale. So when you adjust for two positions, automatically for the third position, that is when the input voltage is 50 and the range switch is in position 50 volts. So obviously this pointer has to be at its full scale mark. So the device is calibrated and is ready for used. So first for with the zero input, zero adjustment is done by this 2.5K, and by using this 10K part, span adjustment is done. That is with full voltage applied, full scale deflection on the scale. Once this process is completed, you can apply any unknown input voltage here, and that can be measured very accurately because the input impedance offered by this arrangement is very high and there would not be any loading effect, and the measurement would be very accurate. And this instrument requires 50 microamperes for its full scale deflection, right? So the circuit can be divided into three main sections: the range attenuator section, source follower section, and bridge circuit section. This is range attenuator part, this is source follower, and this is bridge. Range attenuator section. It is a potential divider circuit with three resistors connected in series. The section is used to select the desired range of voltage in 500 millivolts or zero point 0.5 volts, 5 volts and 50 volts range. Out of these three ranges, we can choose any one range, just like this. 0.5 here, 5 here and 50 here, and this range switch can be connected to any one of the three positions. Accordingly, the input voltage will change. Input resistance will change. For 0.5 volts position, the input resistance is 1 mega ohm. For 5 volts section, the input position, the input resistance is 9.9 plus 1, 10.1 mega ohms. And for 500 volts position, it is 9.9. Sorry, for 5 volts position, it is 9 plus 1, 10 mega ohms. And for 50 volts position, it is 9.9 plus 1, 10.9 mega ohms. The second part, a single pole three-way rotary switch is used to select the required range of voltage. This is single pole three position rotary switch. Rotary switch means just like a potentiometer type rotary arrangement. Instead of smooth moving, it would be in three ranges, just like our fan regulator. Fan regulator would be having five ranges, 0 to 5, 1, 2, 3, 4, 5. Here it is simply 0.5, 5 and 50, three ranges. The rotary switch is connected to the gate of a FET by 1 mega ohm resistance used to limit the gate current. Of course, this we have already discussed. Here, 1 mega ohm resistance. Next, source follower section. Q1 transistor is connected in source follower configuration and Q2 transistor acts as its load. Q1 is FET, field effect transistor, and Q2 is BJT, bipolar junction transistor. A source follower drives an emitter follower. FET drives BJT used in emitter follower. The source follower configuration is used, and here one point to be observed. Both the source follower as well as emitter follower, the input impedances will be very high. Based this, you should have studied in earlier classes. I mean, in earlier semesters. If FET operated in source follower mode provides very high input impedance, and emitter follower, that is BJT operated in emitter follower mode, provides very high input impedance. So this also contributes to the high input impedance of the circuit, increasing the sensitivity of the device. The source follower configuration is used to provide impedance matching, thus delivering maximum power to the load and thereby providing high accuracy. Here, this is source follower, emitter follower. Why emitter follower? Because the remaining circuitry is connected at the emitter, not at the collector. So whatever is the potential at the gate, the same would be the potential at source. Whatever is the potential at source, the same would be the potential at base of Q2. Whatever the potential at base of Q2, the same would be the potential at the emitter of Q2. From here, gate to source, the resistance is very high because it is in source follower mode. From base to emitter, the resistance is very high because it is in emitter follower mode. So already high input impedance followed by 1 mega ohm followed by high input impedance because of source follower gate to source, high input impedance because of emitter follower from base to emitter. All these contributes to sensitivity of the instrument. The transistor Q2, its emitter resistance of 10 kilo ohms, the 2.5 kilo ohm potentiometer and 2.2 kilo ohms resistor act as 4 arms of a bridge circuit. A 10K calibration part and a microammeter are connected between the diagonal points of the bridge. These are called the output terminals of the bridge. The power supply is connected to the circuit by means of a switch S. Here, by means of the switch S, 4.5 volt supply is connected to the bridge circuit. And 10K part with a microammeter forms a voltmeter. Next, working of a FET input voltmeter. The working of a FET input voltmeter can be described under the following sections: zero adjustment, calibration, and actual measurement. Zero adjustment. First, select the required range of voltage by a rotary switch. Then short the two test terminals. When the switch S is closed, the drain current and hence the emitter current emitter current flows in the transistor Q2. The microammeter shows some reading. That means here you have to select any one range, close this, then whatever is the current flowing here, the same would flow here and the same would flow here. Point, the meter will indicate something. In order to make ammeter to indicate zero deflection, the zero adjustment part is carefully adjusted. The bridge circuit is set to be in balanced position when the meter reads zero. By adjusting this potentiometer, this bridge is brought to balance condition. That is, the potential at this terminal will be equal to the potential at this terminal. As a result, there won't be any potential difference across the microammeter. So naturally, no current flows through the meter and the pointer would be set to zero position. By adjusting this part, by connecting this switch to any one of the ranges and by short circuiting this. Thus, that is called as zero adjustment. Second one is calibration. The short circuit between the two terminals is replaced by a known voltage source. The 500 millivolts range is selected by the rotary switch. The known voltage causes some current to flow in the transistor Q2. This results in a voltage drop across the emitter resistance Re. This causes a deflection in the micrometer. The 10 kilo ohms calibration part is adjusted until the meter reads full scale deflection. Suppose if I select 0.5 volts range, so with 0.5 volts at the input, 10K part is adjusted till the micrometer shows full scale deflection. Similarly, with 5 volts range, then also the same procedure can be used, and the pointer has to be showing full scale value. In any one of the position, this span adjustment is sufficient. That is adjustment of 10K part to full scale position. Naturally, if it is set in one position, one switch range, either zero point 0.5 volts or 5 volts or 50 volts, in the remaining two positions also it has to show full scale. If at all not showing, slight adjustment may be required. Now the meter is ready for the measurement. Actual measurement. Apply the unknown voltage between the two test terminals Q1 and Q2. The micrometer then deflects in proportion to the unknown voltage. If the rotary switch is in 500 millivolts range, that is 0.5 volts range, reading can be had directly. If it is in 5 volts range, the reading should be multiplied by 10. Right? When the range switch is changed to second position, the reading actually would be zero point 0.5. It has to be multiplied with 10, second range. And in the third range, 50 volts range, it has to be multiplied with another 10. For 0.5 to 5, multiplication with 10. Similarly, 5 to 50, multiplication with 10. If it is calibrated in zero point 0.5 volts range, the scale would be from 0 to zero point 0.5. So naturally, for 5 volts range, we have to multiply each value by 10. Say for example, the unknown voltage is applied and the range switch is selected to be 5 volts one. The pointer is showing zero point 0.3 volts. Then we have to read it as 0.3 into 10, that is 3 volts, not 0.3 volts. Or suppose the range switch is selected to be 50 volts and unknown voltage is applied and the pointer is showing say 0.1 volts. In that case, it has to be read as 0.1 into 100, that is 10 volts, not 0.1 volt. Right? That is how the measurements are to be taken using FET input voltmeter. This is for DC measurements. For AC measurements, the AC voltage is first converted into DC voltage with the help of a rectifier. The rectified DC is applied at the input terminals of the FET input voltmeter. Only change is a rectifier is added prior to the FET input voltmeter, and of course the meter is average responding device. It responds to the average value of the reading, input voltage. If the rectifier is halfway rectifier, then you will get somewhere around 45% of the average value when used directly. 45 or 65, I think 65. When used, when a full wave rectifier is used, you will get 90% value DC. in place of 100% when used directly for DC measurement. Drift problem in FET voltmeter. This is one point to be kept in mind while using the circuit. Drift problem, that is the effect of temperature. The drawback of FET input voltmeter is that it has to work under specified ambient temperature conditions only. Specified ambient temperature conditions only. The manufacturer will give a range of temperatures under which it will provide accurate measurements. Say for example 25 degrees to 40 degrees or 0 to 40 degrees. A range is given by the manufacturer. If we are using the instrument at high temperatures or low temperatures, there would be a drift in the voltage. There would be a change in the resulting current in the circuit, and the measurement also will be slightly in error. Drift means change in the measured value. So here, under specified ambient conditions, temperature only we have to use to get better accuracy. Otherwise, excessive drift problem occurs during operation with change in ambient temperature. When there is a change in ambient temperature, say higher value or lower value, automatically the voltage measurement would also be changing. And the advantages of a FET input voltmeter, same as the advantages of electronic voltmeter. Basically, a FET input voltmeter also is an electronic voltmeter. So, high input impedance to isolate meter from the measurement circuit. Power consumption is less. Overloading does not damage the meter. These are the main advantages. And of course, this circuit can be used for wide range of frequencies also, starting from zero frequency, that is DC, to a high value of AC also. So what we have studied is, we studied about electronic voltmeters, different types of electronic voltmeters. One such electronic voltmeter is a FET input voltmeter, and we have seen how the circuit is developed or constructed and what is the working of FET input voltmeter, how it is to be used and how it works. So this is all about FET input voltmeter. In the next class, we'll see another type of electronic voltmeter, that is differential voltmeter, right? That we'll see in the next class. Thank you.